Okay, well, now that we know about arrays and we've introduced the for loop, which is a convenient tool for stepping through items in an array, we're going to get a little more deeply into arrays and introduce the idea of pointers, which point to items in memory, or in the case of arrays, point to elements within an array. We're also going to take a look at the default call by value argument passing behavior of C++ functions, and we're going to see that you can pass an address of an object by value into a function in order to enable that function to change the object. Okay, so from the last lecture, we know that elements in an array are always stored in ascending contiguous memory locations, that is, side by side in memory. Here we have 3 example arrays. CA is an array of 7 chars. So the initial char of CA is going to be at some address in memory. The next element in CA is going to be 1 byte further along, 1 byte higher in memory in terms of its location. And altogether, this array is guaranteed to take exactly 7 bytes of memory, since a char is 1 byte by definition. IA is an array of 4 ints. On our machines, an int is 4 bytes wide, and so an array of 4 ints is going to occupy a total of 16 bytes of memory. DA is an array of 3 doubles. Again, on our machines, a double is 8 bytes wide, and so an array of 3 doubles is going to occupy 24 bytes of memory. Here on slide 3 is a repetition of an example program that we looked at in the previous lecture, showing that it is possible to go outside the bounds of an array in C++, and neither the compiler nor the runtime environment will warn you or protect you from that. So the output that we might get from this program is, let's see, in each element of the array here, we're multiplying it by 3, going from item sub 1 up to item sub 2, 3, 4. And that 4th element is actually 1 past the end of the actual array A. So our output, produced by the second for loop, definitely we're going to have 9, 15, and 21 for A sub 1, 2, and 3. And then we may get some garbage for A sub 4. Or we may get a crash right at that point. We should consider ourselves lucky if our program crashes right at that point, because that will help us isolate our bug. Okay, any object, and for that matter any function, is located in memory at some address. And the address is typically going to be the address of the first byte of the object. You can obtain the address of an object in your C++ program by sticking the ampersand operator in front of it. And we'll pronounce the ampersand operator as the address of operator. Let me skip ahead to an example program here. So here, in slide 6, we're putting an ampersand in front of x. X is a double object initialized with this value 1.234. So ampersand x gives me the address of x. Specifically, that's going to be the address of the first byte of that 8-byte object x. And when I display that using cout, cout by default will display that as a hexadecimal number, a base 16 number. So let's take a look at what's going on with this program here on slide 6. Here are my elegant diagrams of what's happening in memory. So x is a double object. X is going to occupy 8 bytes of memory, specifically in a part of memory called the stack, although we'll worry about that more later. And x has been initialized here with 1.234. So the bit pattern representing a floating point 1.234 is going to occupy the 8 bytes, that is the 64 bits of memory in X. J here is an int object initialized with 89. J on our systems is 4 bytes, so it's half as many bytes as a double. And it's going to contain the bit pattern representing the integer value 89. A here is an array of 4 ints. These have been initialized with 2, 3, 5, and 7. So the array A is going to be exactly 4 times as many bytes as the individual int J, and each of the elements in A is going to be represented or going to contain a bit pattern for 2, 3, 5, and 7, respectively. When I ask for the address of X, what I'm going to get is the memory address of the first byte of that 8-byte thing called X. Then when I move on and ask for the address of J, I'm going to get the address of the first byte of that int object J. And later, here I'm asking for the address of the element of A sub 0, and also the address of the element of A sub 1. All right, so A sub 0 is this int, this 4-byte int containing a 2, and address of A sub 0 is going to be the address of the first of those 4 bytes. Address of A sub 1 is going to be the address of the first byte in A sub 1, that is the int that's currently containing a value of 3. If I actually run this program, let me skip to my Ubuntu window, and actually let me put the program over here on the left side. Okay, so there's the program on the left side, and now let me run the program. This is called addresses.cpp. Okay, this program I'm showing in my right-hand Ubuntu window is the same as what we have on the left, except that I've added the include directive and the using namespace line. All right, so I'm going to compile this thing, if I can type. And I will run it. And there we are. So I get told that X is at address, and then I get this hexadecimal location. Now, the specific address here, 0x7FFF blah 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 68, is not very meaningful. So in diagrams, typically what I will do is to use an arrow to indicate that this expression, in this case, ampersand A sub 1, has as its value an address of some object. Having an arrow that points to the first byte in the object is more meaningful than writing down that, okay, well, in our case, in our case, that arrow is actually hexadecimal 7FFFF3F39F74. Okay, it's more meaningful to understand the address of A sub 1 points to the first byte of the item A sub 1, the element A sub 1 in this array A. I do want to point out something about these addresses, though, which is their relative values. Notice that J is at some location ending in 6.4. X is at some location ending in 6.8. That means there are 4 bytes separating the beginning of J from the beginning of X. Now, that actually makes sense. J is an int, X is a double, so we would expect J to require 4 bytes of memory before X starts. Notice down here that A sub 0 starts at the same address except 70 rather than 68. Recall that these are hexadecimal numbers. So hex 68 means a 6 in the 16s position and an 8 in the 1s position. If we add 8 the 8 plus 8 is going to give me a 16, and consequently in hex, 6, 8 plus 8 is 7, is 7, 0. All right, so that indicates that J comes in memory first, starting at this position, ending in 39F64. Then X starts 4 bytes later, 39F68. And A sub 0 starts 8 bytes later, 39F70. A sub 1, which is the next int, all right, each int element is 4 bytes wide. So A sub 1 starts at location 39F74. Okay, so the specific value, hex 7, FFF, blah, 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 isn't really that meaningful, but we can tell how memory is being laid out here for the local variables in this function. We can see that J has been stored first, 4 bytes later X is stored, 8 bytes after that, that is 1 byte past the end of X, A sub 0 is stored, immediately followed by A sub 1. We know that array elements are stored in ascending contiguous memory locations, so we can know that A sub 2 here, containing the 5, starts at the address ending in 39F78. Okay. On slide 7, I'm showing some different representative output. The exact numbers here are not the same as the exact numbers that I got on my machine this time, but the relationship among these values is the same. J is stored in memory at some location. X is stored in memory 4 bytes later. A sub 0 is stored in memory 8 bytes later. And A sub 1 is stored in memory 4 bytes after A sub 0. Well, we can now get the address of an object by sticking an ampersand in front of that object. That's all very nice. How do we make use of that address? How can we follow that address back to the thing that the address is pointing to? Ampersand is what we're calling the address of operator, and the inverse of ampersand in C++ notation is star, used as a unary operator, not star like multiplication. Star is called the indirection, or informally the contents at operator. So if you have an address, you can obtain the contents at that address by sticking a star in front. All right, so in this little chunk of code, we have this variable I initialized with 9. It's an int. The value of I is just going to be a 9. Let me display some example output there. So the value of I is going to be 9. Now, that variable I is going to be stored at some place in memory, and I can find out where that thing is in memory by using the expression ampersand I. And let's suppose that we get this as the hexadecimal representation of that address. It doesn't really matter. Now, in order to get the contents at that address, given the address, I stick a star in front of the address, and what I'm getting here is the contents at the address of I, which is the same thing as I's value. It's sort of like asking, who lives at the address of Jane? Well, who lives at the address of Jane is Jane. So here, the contents at the address of I is I, and the value of I is 9. Now, in order to carry around an address in a variable, we have to know how to declare what are called pointer variables. And to declare a pointer variable, we use the star in the declaration. This notation is referred to as the declaration mimics use notation for declarations of pointers in C++, and it is a It is a hated aspect of C and C++, but it's one of these things you just have to get used to. So if I have, let's say, an int, and I want to declare a pointer to an int, I write down the name of my pointer variable, and in front of that I put a star indicating pointer to, and in front of that I say int, indicating the type of thing that the pointer is pointing to. This is a pattern of reading that I'm going to use over and over and over again until you're well sick of it, that I call the right to left style of reading type declarations. It's actually going to turn into the inside out right to left notation. All right, so this declaration here says that P is an object, it's a variable, whose data type is pointer to some type, like pointer to int, pointer to baboon, pointer to double, pointer to char, whatever it might be. Like any other object, the variable can be either initialized or uninitialized. You should initialize a pointer if you know the address that you want the pointer to point to. You can also assign the address of something to that pointer variable, assuming that the something whose address you're getting is the same data type that the pointer is expecting to point to. So let's see some code. Here I have another program. Actually, as I did before, let me put my program on the left-hand side so that I can pull up my Ubuntu window on the right. This thing is called morepointers.cpp, so morepointers.cpp. And there we have it. I have added the include of IOStream and using namespace standard. Otherwise, this program is the same as what I have on the left. When we run this program, the local variables get created, and in the cases where they are initialized, the initialization takes place. Rather than me drawing a diagram of all the local variables at once, let me create the variables and initialize them according to the order of these declaration statements. So here are my elegant diagrams. J is an int whose initial value is 4. So J has 4 bytes of storage allocated for it, and the bit pattern for 4 is stored in J. Now P1 here, notice I'm reading this thing from right to left. P1 is a pointer to an int. That is, the variable P1 can contain the address of some int object, but it's uninitialized. Consequently, although P1 exists, we don't know anything about the contents. The contents are undefined. One question to ask at this point is, how big is P1 in memory? We know that a char is 1 byte. We know that on our systems an int is 4 bytes and a double is 8 bytes. How big is a pointer to an int? Well, the answer is that it is big enough to contain any valid address on our machine. Since we are using 64-bit processors, it turns out that a pointer is a 64-bit size, that is an 8-byte size object. However, we don't usually care about the actual bit pattern stored in a pointer object. And in diagrams, I'm going to put in my pointer objects pointers, arrows, to other objects, rather than representing some kind of bit pattern. So I typically draw pointer objects simply to be a different size from ints, to indicate that they're not exactly the same size as an int. In this case, actually, they're twice as big as an int, but that doesn't really matter. All right, so P1 is a pointer to an int, and it's not initialized. So the next thing we're going to do is an assignment statement in which we're going to compute the address of J and assign the address of J into P1. So that's going to cause P1 to point to the first byte of J. All right, and so this is what I'm talking about. I just draw an arrow from the pointer variable to the first byte of the object that the pointer is pointing to. Now, rather than create P1 and then assigning a value to P1 in a second step, in the declaration of P2 here, I am both declaring what data type P2 is and providing an initial value for P2 in an initialized declaration statement. So this says, again, reading from right to left and then reading the initialization part, P2 is a pointer to an int. The initial value of P2 is the address of J. All right, so this statement is doing two things. First of all, it's declaring the data type of P2. P2 is a pointer to an int. Secondly, it's specifying the initial value for P2. P2 is initially the address of J. So in our diagram, P2 is also a pointer to an int, and it is also pointing to J. So it contains the same address bit pattern that P1 does. Here, for P3, I'm simply using a different style of initialization notation, namely the parentheses rather than the equal sign. P3 is also a pointer to an int. P3 is initialized to contain the address of J. And so here is P3. Okay, so when we run this program, J gets created, P1 gets created uninitialized, but we then assigned the address of J into P1. P2 is created and initialized to point to J. And P3 is also created and initialized to point to J. So in this cout statement here, I'm going to display the address of J. The value of P1 had better be that same address, right? Up here we said P1 gets the address of J. So if I display the address of J, and then I display P1, those had better be the same hexadecimal values. Likewise, P2 and P3 had also better be the same hexadecimal values. Let's take a look at the example output. All right, so here we have our representation of the address of J, and we have the same hexadecimal value for P1, P2, P3. Let me show you on my system that works. I'm going to save this and compile it. Oops, more pointers. And run it. Okay, so these addresses are longer, but notice I do have hex 7, FFF, blah, 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 088C, 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 088C. Okay, so the address of J is the same as the value of P1, the value of P2, and the value of P3. The final bit of code, the final statement is printing the value of J and the contents at P1, the contents at that address P1. In other words, we're going to follow P1 to the thing it points to, which is J, and we're going to display the value of J, the value of the thing that P1 points to. Then the value of the thing P2 points to, and the value of the thing P3 points to. All right, so J, the contents at the address where P1 is pointing, contents at P2, contents at P3, all of these had better be the value of J, which is 4. And indeed, that's what we got, 4444 as our output. Okay, so pointers are used for indirect access to other objects or to functions. And pointers in C++ are the key to creating linked data structures of all kinds. We have singly linked lists, doubly linked lists, binary search trees, balanced binary search trees, circular lists, hash tables, decision lists, decision trees, Bayes networks, all of these kinds of things can be created using pointers from one object to another. Okay, the next thing that we're going to take a look at is the default call by value argument passing mechanism that C and C++ use to pass values into functions. When you call a function, right, for example, here in main, I have two int variables, I and j, that have been declared and initialized, and I'm calling this function named swap with the variables I and j as arguments. When you call a function, copies of the values of those arguments get passed into the function, and those become the initial values of parameters. So here is where I'm calling the swap function in main. In the definition of the swap function, I have two parameters, a, which is an int, and b, which is an int, that receives copies of those values for I and j. Now, the parameters are in separate memory from the variables in the calling function. This is wholly unlike Python, where the parameters here would just be references to the same objects that I and j are references to. But in C++, I is the name of a specific object at a specific location in memory. J is likewise the name of a specific object at a specific location in memory. And copies of I and j, that is the value 3 and the value -5, get passed in and become the initial values of these parameters a and b, which occupy separate memory. Okay, so here are my elegant diagrams coming up. When I run my program, whose name, by the way, is swap1, main is called first, and in main, the first thing that happens is that storage is allocated for these two variables I and j. Each of these is an int. I is initialized to contain 3. J is initialized to contain -5. This may be the first example that we've seen of creating and initializing two variables of the same data type in the same declaration. I'm simply using a comma to separate the fact that I is an int initialized with 3 from j is also an int with an initial value of -5. Okay, so storage gets allocated for those and initialized with 3 and -5. Then we're going to display the value of I and the value of j. That just produces a line of output. And after that, we're going to call this function swap, passing in copies of these values of I and j. So a value 3 gets passed in as the first argument. The value -5 gets passed in as the second argument. We've been careful to define swap above main so that when the C++ compiler sees swap being called down here, it knows what the interface for swap looks like. Swap is a function that expects to receive two int parameters. The first will be called a, the second will be called b. Swap does not return a value, so its return type is declared as void. Now, space is being allocated for these parameter variables a and b, and those parameter variables are initialized with copies of the values of I and j. So this is our situation now. In main, we have these variables I and j containing 3 and -5 respectively. In swap, we have separate parameter variables, a and b, containing 3 and -5 at this point. Okay, now we're going to execute the statements within the swap function. The first statement within the swap function is creating a local variable called temp, containing an int, and we're initializing temp with the value of a. So a copy of that 3 becomes the initial value of temp. All right, and so there we are. That's the first executable statement within the body of swap. We've declared and initialized temp. The next statement is this assignment in which the value of the variable b, minus 5, is being assigned into a. That means that the current value of a, which is 3, is going to be written over by the bit pattern representing minus 5. And so here's the result of that assignment statement. Little a no longer contains the bit pattern for 3, now it contains the bit pattern for minus 5. Notice that that didn't have any effect on the I or the j variable back in main. The third statement in swap says b gets temp, so that's going to take the value of temp, which is 3, and overwrite the bit pattern that's currently in b. All right, so b now contains 3. When we hit the closing curly brace of the swap function, the swap function will return back to whoever called it. It turns out that the parameter variables and local variables for the swap function are erased from memory at this point, although I don't have a diagram showing them being erased. But those variables are now gone from memory, and we come back to main and execute the next statement in main, displaying the value of j. They're displaying the value of I and displaying the value of j. And our swap function, despite its name, has not actually done anything to main's variables I and j. Okay, so that illustrates the idea of call by value. Copies of the values of the arguments get passed into the called function, and those copies of those values become the initial values of parameter variables stored in separate memory. Well, that raises an obvious question, which is, how could we write a swap function that actually works, that does swap the value of main's I with the value of main's j? To do that, we're going to come back to pointers. Okay, so what we're going to do, instead of passing copies of the values of a couple of variables, we're going to pass copies of the addresses of those variables. And we're going to have pointer parameters in the called function. This is a different implementation of the swap function to receive these addresses that we're passing. So notice the change that we've made in main here on slide 17. We're passing the address of I as the first argument to swap and the address of j as the second argument to swap. That means that the parameters have to be declared to receive those addresses. P1 is declared as a pointer to int. P2 is also declared as a pointer to int. So P1 receives the address of I. P2 receives the address of j. We can then indirectly access mains I and j through those pointers P1 and P2. Here's how that's going to look in terms of diagrams. Once again, my fancy diagrams. All right, so initially, when we run our program, main has these two int variables, I initialized with 3, j initialized with minus 5. When we call swap, the address of I gets passed down and becomes the initial value of P1 in swap. The address of j gets passed down and becomes the initial value of P2 in swap. So here's what we have now. Of course, P1 and P2 actually contain bit patterns representing the addresses of main's local variables I and j, but it's easier to understand if we just draw arrows from P1 to I and P2 to j. Okay, so now we're executing the statements within swap. The first statement within the body of swap declares an int variable temp, and that variable temp is going to receive a copy of the object that P1 points to. All right, so star P1 is indirectly accessing I, or more correctly, I should just say I rather than the address of I. So star P1 is the value of I, which is 3, and that's what goes into the temp variable in that blue statement in swap. The second statement in swap says star P1 gets star P2. All right, so P1 is pointing at I. Star P1, therefore, is I. And now what I'm saying here is mains I gets star P2, well, star P2 is mains J. So mains I is going to get the contents of mains J. That means that the 3 that was in I, that is, that was in star P1, is going to get replaced with the -5 that is in star P2. And therefore we have this situation now. The final statement in swap says star P2, well, star P2 is the variable J back in main. Star P2 gets the value of temp, which is 3. All right, so the -5 in J gets replaced with a 3. At that point, we hit the closing curly brace for our swap function. The swap function returns, and although I don't have a diagram that shows this, swap's parameter variables and local temp variable are all eliminated from the stack, and all I have left when I get back to main are main's local variables I, which now contains a -5, and J, which contains a 3. Okay, so that's how we can use a combination of pointers with the call by value argument passing to cause a function that you call to change variables back in the calling function. Swap was able to change variables in main. All right, well, the last thing that we're going to mention here is that array names are very tightly connected to pointers. In fact, the name of an array actually denotes the address of the initial element of that array. That is, if CA is an array, and let me go back to where we declared CA, way back on slide 2 is where we declared CA. So CA is an array of 7 chars, and CA all by itself, just the name of that array, denotes the address of that array's initial character. In other words, CA is really like a shorthand for address of CA sub 0. Likewise, IA here is an array of 4 ints. IA is simply a shorthand for the address of IA sub 0. And DA is a shorthand for the address of DA sub 0. All right, so we can flip this idea around in the other direction. If the name of an array is a pointer to the initial element of the array, then let's suppose that we have the address of some object like a zebra somewhere in memory. That is, we have a pointer to zebra data type. Well, that pointer can be thought of as the address of the initial element of some array of zebras. Okay? And if you add an offset to that pointer, what you get is the address of the nth element within that array of zebra. That is, the addition to a pointer of some integer offset is scaled by the size of the thing that the pointer is pointing to. All right, so if I have an array of zebra, I don't even have to know how big each zebra is myself, because the compiler knows how big each zebra is. And if I have a pointer to one zebra and I add one, I get a pointer to the next zebra in memory. And if I add one more, I get a pointer to the next zebra in memory, and so forth. Okay, so here on slide 21, we have a repetition of slide 2 with our arrays being declared and diagrammed. CA is an array of 7 chars. CA sub 0 is the initial char in that array of 7 characters. Ampersand of CA sub 0 is the address of that initial char. Likewise, IA is an array of 4 ints here. IA itself is a pointer to the first int in the array. DA is an array of 3 doubles. DA is a pointer to the first double. And to amaze you with more fancy diagrams, okay, so address of CA sub 0 is the address of the initial char in that array. Address of CA sub 3 is the address of the sub3 element, that is the fourth element in that array of chars. In fact, if I go beyond the end of the array, recall that C++ does not do any array bounds checking. The address of CA sub 9 is not within the bounds of the array CA, but it is at some very well-defined location. It is the address of the char that is 3 chars past the end of the array CA. Now, if I were to assign a value to that location, I could potentially cause myself some very great problems. For example, in memory, if IA happens to immediately follow CA, then this third char after the end of CA, that might be the third byte of the first int within IA. So I definitely don't want to mess around with whatever is at that location, but the location is very well defined in the C++ language. So address of IA sub 0 is the address of the first byte of the first int within IA. Address of IA sub 2 is the address of the first byte in the sub 2 item, the third item of IA. Address of IA sub -1, again, this is not within the bounds of the array IA, but it is very well defined what it means. It is 1 int's worth of memory prior to the beginning of IA, so the address of IA sub -1 is the address of this byte that's 4 bytes sooner than the beginning of the array. That is, that's 4 bytes earlier than IA sub 0. And again, we're relying on the fact that on our systems an int is 4 bytes wide. All right, and then finally here we have the address of DA sub 0, the address of DA sub 2. Okay, so to sum up, the name of an array is a pointer to the initial element within the array. If I have a pointer variable, I can think of that pointer variable as pointing to the first element within an array. In this particular example, that's exactly correct. A here is an array of 4 ints. P is a pointer to an int initialized with A. Recall that A, the name of the array, is simply a shorthand for address of A sub 0, so P is pointing at the first int within the array A. And when I do a subscript on an actual array name, that's going to be equivalent in this case because P is pointing at the same location to using a subscript on the pointer itself. All right, so in other words, taking the name of the array and adding an offset of n, the compiler will scale that by the size of an int. So A is going to be a pointer to the first int. A plus 1 is going to be 4 bytes further along, a pointer to the second int. A plus 2 is going to be 8 bytes further along, a pointer to the third int, and so on. Obviously, if P is also pointing at A sub 0, then P plus n is going to be pointing n ints further along in memory. And star of that is the integer object, the int object at that location in memory, which in turn is P sub n. So it turns out really that this subscript notation is just what's called syntactic sugarcoating for adding an integer offset and then doing an indirection on that offset. All right, so pointers and arrays are very tightly interrelated, and this is going to be very important to us in understanding C++.